All right, so welcome back. This is going to be Chapter 3. In Chapter 3, we're going to take a look at something called linear programming. We're going to start out by taking a look at Section 3.1, where we're going to graph linear inequalities. And our goal here is to get to something called linear programming. Now, linear programming is similar to the Lagrange multipliers we did, where we had a function we wanted to maximize or minimize subject to some constraints. And we're going to do that kind of again. So it's similar to that. It's just this time when we take a look at it, everything that we're going to look at is going to be linear, meaning we're going to be dealing with linear functions. So those multivariable functions we had earlier, where we had x's and x squareds and y's and y squareds, and we took derivatives, we won't be doing that. We're working with linear functions. All right, but to get started, though, we have to take a look at Chapter 3, which is going to be the graphical method for linear programming. So we need to take a look at graphing. Okay? And so in this section, we're going to be graphing linear inequalities, and then from that, linear systems. Okay. So first off, what is a linear inequality? Well, a linear inequality is going to be an inequality that contains two variables and takes on one of these four forms right here. It's either going to be ax plus by is less than or equal to some value c, greater than or equal to some value c, strictly less than or strictly greater than. And I will tell you that in this chapter, in this course, we pretty much live only with these two right here. We don't do very much with the strict inequalities, the strict less than and the strict greater than. It's mostly the less than or equal to or greater than equal to. Okay? You notice that these are kind of written in general form. That is, we have the variables on the left and then the constant on the right and the inequality. So we have the algebra over here. And then we have a less than or equal to or greater than equal to, and then we have a number over there. Okay, so the variables on the left, the constant on the right. Okay? Even though every single one of these is written as having an A and a B, so you could have an X and a Y, you could have either A or B both be either A or B be zero. They wouldn't both be zero. It would be a really boring inequality then. Okay? All right, so what we're going to do with those things is we're going to graph them. And so here's the terminology that we're going to be using. We're going to be talking about graphing something called the boundary or the boundary line. The boundary or the boundary line is the line that is formed from the inequality by removing the inequality symbol and replacing it with an equality symbol. Okay? So the boundary line would be if I had the equation 4x plus 3y was less than or equal to 12, the boundary line would be 4x plus 3y equals 12. And that's the line that we're going to graph that's going to allow us to graph the feasible region of the inequality. And the feasible region is the region in the plane. Think of a region as a part of a plane. A part of a plane that satisfies all of the inequalities in your system. So if your system only had one inequality, it would just be a half plane. If it had more than one inequality, then those boundary lines and those solutions or those solution sets for those inequalities can reduce down your part of the plane that works to a smaller and smaller feasible region. Okay? Feasible regions can be called bounded or unbounded. Bounded is if they have edges all the way around that enclose them. Unbounded would be if one side somehow opened up to infinity. And then the other piece of terminology we'll be using are corners. Corners are going to be intersections of boundary lines. Right? So what's going to happen is we're going to have some sort of system of inequalities. Now, one of the other things that this section uses a lot is we end up with graphs where we only care about the first quadrant. So you're going to get some inequality that's going to give you a boundary line. And let's say that that boundary line gives us this piece right here. let's say that the scenario that surrounds the problem tells me that x's can't be negative, y's can't be negative, and then sum ax plus by is less than or equal to, I don't know, pick a number, C. And so this boundary line right here is going to be that boundary line. And because we're smaller, we want that inside piece over there. And then we say, okay, everything inside of that triangle is going to be our feasible region. And then our feasible region is going to have 3 corners because they are the intersections of the boundary lines. They might be thinking, I don't see boundary lines. I only see a boundary line. Well, this one, where x is equal to 0, is the y-axis. And this one, where y is equal to 0, is the x-axis. And so there's technically 3 boundary lines here, which gives us our feasible region and gives us 3 corners. Now, if we added in a second inequality, and let's just say we added in the inequality, I don't know, I've already used a, b, and c, so I'll use, I don't know, dx plus ey is less than or equal to f. Oops, that's not an f, that's an e. F, this was a c. Then that would give us another boundary line. Let's just say that that one gave us this boundary line. Okay. And let's say that the inequality gave us the piece underneath it. So then we'd be here. But the problem is for my system to work, I want to know where are not just the green good, but where is the green and the pink good. So I'm going to get a new feasible region that's going to have these corners and an even smaller piece that works. Okay. It's going to be limited partly by the pink line, partly by the green line, and together it's going to give us this weird feasible region. There. Okay. All right, so what we're going to need to be able to do is we're going to need to be able to take a system of linear inequalities and graph it. Not only do I have to be able to graph it, but I have to be able to find all of those corners of those feasible regions and all of that business. It's going to be a blast. So the feasible region, the corners, all that we got to find, and then we're going to make this happen. All right, so we're going to start with an example here. I have an example where I have a system of inequalities, and my job is to find the feasible region and then tell whether it's going to be bounded, like closed in on all sides, or unbounded. All right, so I'm going to go ahead and just make a quick sketch, and I'll graph these. I'm going to call these equation 1 and equation 2. So the boundary line for 1 is going to be x plus y equals 1, which means it's going to have an x-intercept of 1, 0 and a y-intercept of 0, 1. Okay, remember to find intercepts, set the other variable to 0 and solve. So if I set y equals 0, then x is 1. Or if I set x equal to 0, then y is 1. The boundary line for equation 2 is going to be x minus y equals 2, okay, which is going to have an x-intercept of 2 and a y-intercept of 0, negative 2. Right? I'll do the first boundary line, or the first one in blue. Okay? So it goes through the 1 on the x and 1 on the y. I know that's the x there and that's the y up there. So there's my boundary line. Because it is a less than or equal to, it is a solid boundary line. It's not dashed. Right? And now I got to figure out which side to shade. So I'm going to pick a test point that is not on the line, 0, 0. I'm going to test it in the inequality. is 0 plus 0 less than or equal to 1. That is indeed true, so that means we're going to shade this entire side over here. Okay. Now I'm going to graph the second boundary line. I'll do the second boundary line in pink, or the second inequality in pink. My boundary line, let's see, it needs to go through 2 on the x-axis and negative 2 on the y-axis. Again, it's a solid line because it is a less than or equal to. I'm going to test 0, 0. Okay. I'll put it into the inequality. Is 0 minus 0 greater than or equal to 2? And the answer to that is no. So that means that the origin does not work. So that means it's this side over here. And so now the question is, what is the feasible region? Well, the feasible region is the part that's shaded pink and blue. So it's this piece right here that satisfies both inequalities. So it's all this down here, and we've got only one corner right there. We only have one corner. Okay? It is an unbounded feasible region because it just keeps going forever in that direction. Okay? And what is that corner? Well, that corner is the intersection of the blue line and the pink line. So that corner is the solution to the system of equations x plus y equals 1 and x minus y equals 2. And let's see, I'll solve this any way I want to. Now, we just got done with an entire chapter on solving these things. So I've got lots of different ways I can solve this. I'm personally going to choose to use elimination. I'll add those two equations together. That gives me 2x is equal to 3. So x is equal to 3 halves. And if x is equal to 3 halves, if I do a substitution, I get that y is equal to 1 half. No, y is equal to negative 1 half, sorry. So that means that that corner is at the point 3 halves, negative 1 half. And so I graph my feasible region. It is an unbounded feasible region with one corner at 3 halves comma negative 1 half. Okay. Let's try another one. Okay. This one's a little more complicated because not just one, but two, but 3 inequalities in our system, but I think we can handle it. Okay. Again, I'm just going to call them 1, 2, and 3. The boundary line for the first equation is going to be x plus y equals 7. It has an x-intercept of 7, 0, a y-intercept of 0, 7. The second boundary line is x minus y equals negative 4. It has an x-intercept of negative 4, comma 0, and a y-intercept of 0, 4. And our third boundary line, that's going to be the line 4x plus y equals 0, has an this is one of those silly ones where I can't just use both of the intercepts because it goes through the origin, so it only has one intercept. So I'll have to make up another point. So I'll make up a point when x is 1, and when x is 1, y has to be negative 4 to make that equation true. Okay. So now I'm going to go ahead and graph these. I'll graph this one in pink, I'll graph this one in blue, and I'll graph this one in green. Okay. The pink one passes through 7, so let's see. My x's and y's have to go out to 7, so I'll put 7 way out here on the end. And it needs to go through those. And then I need to figure out which side to shade. Well, I'll test the origin. Is 0 plus 0 less than or equal to 7? That's true, so that means for this one, I'm shading, oh, I want this one. I'm shading this side down here. Now I'll do the blue one. Okay. It's going to go from negative 4, so if that's about there, about negative 4, to positive 4, so maybe about there. I'll test the origin. Is 0 minus 0 less than or equal to negative 4? That is definitely not true. So that means we don't want the origin side, we want the other side. So we're up to there. Now if I was done there, it would just be where it's pink and blue, but I still got to do the green one. Let's see, the green one goes through the origin, and then the other point was when x is 1, y was -4. And so it's this boundary line right here. And it looks like somewhere up there, maybe off my graph a little bit, but those two would intersect and give us a corner. Okay, so now the question is, which side do we want? So let's see, I'm going to check, let's see, I can't check the origin, so I have to check some point that is not on the curve. So I don't know, that point looks like it's not on the curve, so I'll check -4, 0. 4 times -4 plus 0, is that greater than or equal to 0? And that's definitely not true, so that point doesn't work, so it must be the other side that we shade. So we're shading over here. So now the question becomes, where did we shade all of them? And I think it looks like, and I'll use my gray marker, it looks like our feasible, maybe I should use something better, I'll use red. It looks like our feasible region is going to be this little triangle here, where it's blue, and it's pink, and it's green. And so it looks like we have a bounded feasible region with 3 corners. Now if I wanted to find those corners, I could go ahead and find them. So let's label them A, B, and C. It looks like A is the intersection of the blue and the green. So if I needed to find A, it's the intersection of the blue line, which is the boundary line x minus y equals -4, and the green, 4x plus y equals 0. And I would just find the solution to that system, and it would give me that corner. And then if I wanted to find B, well, B is the pink and the blue, so it's going to be x plus y equals 7, and x minus y equals -4. And I'd find that solution, it would give me B. And then C is the intersection of the pink and the green, so it's going to be x plus y equals 7, and 4x plus y equals 0. And I would find the solution to that system, and it would give me that intersection for corner C. All right, so I'm going to stop this video here. We're at almost 18 minutes. We'll come back and do more of this in video number 2.